Hi everybody, I am Ayman from A to Z Physics. In this video, we are going to talk about the third part of the atom. But first, please don't forget to subscribe to our channel and to activate the bell button to watch every new video. Let's first define the ionization energy of the atom. It is the minimum energy needed to extract an electron from the atom. Ionization always equal to E infinity minus E of the initial state of the atom. For a hydrogen atom in the ground state, ionization energy is equal to E infinity, which is 0, minus E1, which is minus 13.6. So the ionization energy of the hydrogen atom in the first excited state is 13.6 electron volt. For a hydrogen atom in the first excited state, E2, the ionization energy is equal to E infinity minus E2 equal to 3.4 electron volt. The atom can make a transition from a lower state to a higher state after interacting with a photon or electron. Let's start first with the interaction between the atom and a photon. A photon cannot cause the transition of an atom from energy level EP to a higher energy level En unless its energy is exactly the same as the difference of the energies En minus EP of the atom. So E photon always equal to En minus E. When an atom initially found in level P receives a photon of energy E photon, 4 cases may arise. First case, if E photon plus EP equal to En, where En is an existed energy level, implies the atom in this case absorbs this photon and reaches level N. If E photon plus EP is different from En, so the atom does not absorb this photon and it remains in level P, so no interaction between the atom and the photon. Third case, if E photon plus EP equal to 0, implies the atom absorbs the photon and reaches the ionized state E infinity equal to 0. In this case, an electron is extracted from the atom with 0 kinetic energy and the atom becomes an ion. Fourth case, if E photon plus EP greater than 0, the atom absorbs the photon and get ionized, but the emitted electron will have a kinetic energy such that the kinetic energy of the electron is equal to E photon plus EP. Let's solve application 6 about the excitation of the hydrogen atom by a photon. Knowing that the energy En of the hydrogen atom corresponding to an energy level n is given by En equal minus 13.6 over n squared, and the hydrogen atom is found in the ground state. Determine the final state of the atom when it receives a photon of the following energies. First part, if the energy of the received photon is 11 electron volt, E photon plus E1 equal 11 plus into minus 13.6 equal to minus 2.6 electron volt. Now let's check if this level exists. En equal minus 13.6 over n squared implies minus 2.6 equal minus 13.6 over n squared, so n equal 2.28 doesn't belong to n, so this level is not exist. Therefore, there is no interaction between this photon and the atom remains in the ground state. Part B, if the energy of the received photon is 10.2 electron volt, E photon plus E1 equal to minus 3.4 electron volt. Since En equal minus 13.6 over n squared, we will have n equal to 2, which is an integer, so the atom passes from the ground state to the first excited state n equal to. Part C, if the wavelength of the received photon is 97 nanometer, first we need to calculate the energy of the photon, which is equal to hc over lambda. By calculating it, we will have 2.04 times 10 power minus 18 joule. Transforming it or converting it into electron volt, we will have 12.75 electron volt. Now E photon plus E1 equal 12.75 electron volt plus into minus 13.6 equal to minus 0.85 electron volt. When we calculate the value of n, we will have n equal 4, and it is integer belong to n, so the atom passes from the ground state to the third excited state, n equal 4, and in this case the photon is absorbed. Part D, if the energy of the photon is equal to 13.6 electron volt, when we add the energy of the photon to E1, we will have 0 electron volt. In this case, the atom loses electron and becomes ionized. An electron is ejected with 0 kinetic energy. Part E, if the energy of the received photon is 15 electron volt, E photon plus E1 equal 15 plus into minus 13.6 equal to 1.4 electron volt. In this case, the atom loses electron and becomes ionized. An electron is ejected with kinetic energy 1.4 electron volt. Or simply, E photon is greater than the ionization energy, which is equal to 13.6 E infinity minus E1. So in this case, the atom loses electron and becomes ionized. An electron is ejected with a kinetic energy, which is the difference between E photon and E ionization, equal to 15 minus 13.6 equal to 1.4 electron volt. Now let's study the interaction between the hydrogen atom and an electron. For an electron to cause a transition of an atom from energy level EP to a higher energy level En, its kinetic energy must be at least equal to the difference of the energies En minus EP of the atom. During one electron atom collision, the atom absorbs from the electron an amount of energy enough to ensure a transition, since the energy of the electron is not quantized as the energy of the photon. The remaining kinetic energy carried by the electron that caused this interaction is equal to kinetic energy initially of the electron minus En minus E. Application 7. Using the energy diagram of the hydrogen atom and knowing that the hydrogen atom is in the ground state n equal 1, determine the final state of the atom and deduce the kinetic energy remained with the electron when it receives an electron of kinetic energy 9 electron volt, kinetic energy 10.2 electron volt, and kinetic energy 11 electron volt. Part A, the kinetic energy of the electron is 9 electron volt, so kinetic energy of the electron plus E1 equal 9 plus to minus 13.6 equal minus 4.6 electron volt. Using the energy diagram of the hydrogen atom, minus 4.6 electron volt is less than E2, which is equal to minus 3.4 electron volt. So no interaction between the hydrogen atom and this electron, and the atom remains in the ground state. Part B, when the kinetic energy of the electron is 10.2 electron volt, when we add this kinetic energy to E1, we will have minus 3.4 electron volt. Using the energy diagram, minus 3.4 electron volt is equal to E2. So the atom absorbs the whole kinetic energy of the electron and makes an upward transition from the ground state to the first excited state n equal 2. The kinetic energy remained with the electron is 0. Part C, if the kinetic energy of the electron is 11 electron volt, kinetic energy plus E1 equal to minus 2.6 electron volt, and also using the energy diagram of the hydrogen atom, minus 2.6 electron volt is between E2 and E3. So in this case, the hydrogen atom absorbs the kinetic energy from the electron that ensures an upward transition from the ground state to the first excited state, and the remaining kinetic energy of the electron will be equal to the initial kinetic energy minus the energy needed to make a transition from E1 to E2, which is equal to 11 minus 10.2 equal to 0.8 electron volt. Application 8. Quantization of the energy of the atom. The energy of the atom is quantized. What is meant by quantized energy? Answer this question using the energy diagram, using a formula En equal minus 13.6 over n squared electron volt, and using the emission spectrum. First, using the energy diagram, the energy of the atom cannot have any value. It can take only some particular values, so discrete energy levels. 2. Using the formula, for n equal 1, E1 equal minus 13.6 electron volt, for n equal 2, E2 equal minus 13.6 over 2 square equal minus 3.4 electron volt, and for n equal 3, E3 equal to minus 1.51 electron volt. The hydrogen atom has a specific value of energy, discrete values. It cannot have any value, so it is quantized. Now, using the emission spectrum, each bright line in the emission spectrum corresponds to a photon of specific wavelength emitted by the atom when de-excited from a higher energy level to a lower energy level. Since the spectral lines are discrete, discontinuous, so the energy of the atom is quantized. Application 8. Emission and absorption spectrum. Knowing that En is quantized, explain why the emission spectrum is formed of lines or it is discontinuous. Each bright line in the emission spectrum corresponds to a wavelength of a certain photon emitted by the atom when de-excited from higher energy level to a lower energy level. So the energy of each atom is quantized, so the spectrum is formed of discrete lines. Knowing that En is quantized, explain why the absorption spectrum is formed of lines or it is discontinuous. Each dark missing line in the absorption spectrum corresponds to a wavelength of certain photon absorbed by gas atom when it is excited from a lower energy level to a higher energy level. The energy of each atom is quantized, so the absorption spectrum is formed of discrete lines. This is the end of the final part of the atom. Make sure to watch the previous parts and don't forget to subscribe and share. Thank you.